So my name is Fred Kim. I'm product manager at HBK, and I'll introduce today the designing and testing aspects in terms of endurance of structural components for electric vehicles. So before we start, allow me just to introduce my company in a few words. So I work for HBK, as I said, in the Prenscia branch, and Prenscia helps engineers deliver durable and reliable products and helps you guys avoid the cost of unexpected failures. This is done through thanks to two software brands, the nCode brand and the ReliaSoft one. We also do training, whether it's like on methodology, designed for reliability, durability, fatigue, etc., or training on software. And in terms of services, we have a material testing lab in Sheffield in the UK for fatigue characterization. And we also have our colleagues from Prenscia Solutions to help you with your projects. So in terms of the software we develop, the standard software we develop, we've got the ReliaSoft on the left-hand side. The very first column is about reliability analysis. So failure data analysis with Weibull++, system modeling with BlockSim, test planning, etc. The column next to it is all about reliability management. So you have XFMEA, XFracas, and things like that to manage risks, your maintenance activities, and your actions. Then we move on to the nCode columns, and the first one is contains the desktop products. So we got Design Life for CAE-based fatigue, GlyphWorks for signal processing, and VibesYs for acoustic and vibration analysis. Then the last column is for data management, and in there you can find Akira, which is a web portal to access the measured data and the engineering apps to democratize the analysis throughout an organization. But during this webinar, we will concentrate on the desktop products of nCode, mostly Design Life and GlyphWorks. So back to the main topic, designing and testing endurance of structural components for electric vehicles. Let me start by asking, what are the electrification engineers doing with our software? So there are three main aspects to it, and all three of them will have a webinar dedicated. So the first one is the one we're discussing today, the mechanical and durability aspects to vehicle electrification. From next week, there will be another webinar dedicated to electrical and signal processing. And then we'll have a webinar dedicated to statistical and reliability aspects. So let me drill down a little bit on the mechanical and durability. So this is made of, so you can view it from different perspectives. First, if we're talking the battery packs, we can look at the vibration-induced fatigue. There are thousands of cells. They're grouped in modules, and those are grouped together to constitute the battery pack. And those cells are often welded together, and those welds suffer from vibration fatigue. But also the combination of lightweight supports structures, right, with the heavy batteries result in mechanical resonances, which themselves lead to fatigue failures. So here we want to run some CAE-based vibration fatigue to optimize the mechanical parts for life, weight, and cost in general. So that's one aspect we'll cover in this presentation. Another one is to do with the design of a vibration profile. As we can guess, vibration can cause catastrophic failures to the battery pack, or more typically, it'll lead to a progressive decline in the battery performances, And the idea here is basically to create a suitable load spectrum, a vibration spectrum that'll be used or could be used in both the battery design that we just saw on top here previously, right? And for the validation testing of the battery pack. So we'll see how to design a representative vibration profile. And last but not least, since electric vehicles require a new design in terms of its body and weight to accommodate for the batteries, we may either go for a new platform or reutilize existing platforms. In both cases, we are facing a number of challenges. Like if we reutilize an existing platform, then we have to check that the weight distribution that has changed, right, due to the batteries. Well, we have to check that this change in distribution of the weight doesn't impact the fatigue life too much, or how much does it impact the fatigue life of the chassis and the body and white in general. And if we go for a new platform, which sounds like an ad hoc solution, well, there's no experience with that. A new platform, and therefore there are risks, and it requires substantial upfront simulations, right, to make sure everything is fine. So we'll cover all three aspects, starting with the most fundamental one, which is based on understanding the loadings that are affecting the different parts of an EV. We'll focus particularly on the batteries, and we'll start with this one also because it serves not only for the validation testing but also for the topic on top, the vibration induced fatigue for the battery packs. So first, you could go for the simpler solution, which is look for a standard, an international standard out there, and for the batteries, right, and use the vibration spectra that are given by this standard. That's one way to go. So I've listed a number of standards here. There are more. So those are the ISO, SAE, IEC, and this US ABC battery test standard. They all refer to lithium-ion batteries, which are indeed commonly used in electric and hybrid vehicles, and they all contain vibration testing procedures, and these are typically defined as PSDs. For those of you who are using our software, you might know we've got a vibration manager where you can find in there a number of those vibration curves from different standards. If the vibration curve you're after is not in there, you can enter your own PSD, sine sweep, sine on random, etc. In there. Once it's in this database in our software, you can use it in a flow file, like I'm going to show you in a minute in a demo. So some of those spectra are in there. So that's one way to do. Just pick one spectrum that seems to correspond to your needs in one of those standards, and just play it on a shaker, or use it as an input to a vibration or frequency domain fatigue analysis. But what we tend to recommend is to get hold of some real data if you can. So you can, what I'm saying is you can derive, you can synthesize, you can design a vibration profile based on in situ measurements, right? So the first thing to do, if you want to go this route, is to understand the usage profile. So you want to know what sort of events you will want to monitor, right, and acquire data from, and what's the contribution of that very event to the whole usage of the car, right? So you have to list all those events and measure them separately. So it's often done in on test tracks, but it could be done also during real conditions, real usage of the car. You just have to section the data corresponding to the various situations extract those data and maybe concatenate them, or there's some editing of the time series to be done. All this can be done in GlyphWorks very easily, our software GlyphWorks. So once you have your measurements and you know the number of repeats for each corresponding to the whole mission profile or usage profile, you have then to go into the second step, which is the actual design of a PSD typically, or a reduced vibration spec that is representative of that. So by representative, I mean it's like in this example where you see a PSD here, it's got a given frequency range, so it's got to be representative of the frequency range you find in your signals. At some frequencies there's more energy than at others. And the very fact that it's a PSD, it means it's random load. In some cases, it might be true. In some other cases, not. So you have to find a representation with its characteristics that are representative of the real loading environment, just like you measured it. And the objective is that this test replicates the same failure mechanisms than in real life. Now, real life is probably a few years, a few 100,000 kilometers, whatever. So you want to reduce that for your validation test to take maybe like 10 or 20 hours or 30 hours maximum, I would say. So you want to accelerate this test to reduce its duration. So that's another route. Indeed, we mentioned the standards. Now we mentioned real measurements, but there is a third way, which is to design your vibration profile from both the standards and the measurements. So if you overlay, for instance, the PSD of your measured data with the PSD coming from the standard, and providing you scale them for same duration so that they're comparable, you might find that at some frequencies, maybe the measured data goes beyond the standard. So if you'd ideally like to take the kind of the envelope of both. Also, you might see, as in this example here, that the measured data covers a wider frequency range that the standard does. So you might as well go beyond the 200 hertz that the standard covers. So you can compare the severity of the various profiles, and then you can synthesize your test specification, taking both into account both of the real measurements and also meet the requirements of the standards. So we'll see how to do that in a demo. All this is done via the vibration profile design module of GlyphWorks. And that would be the recommended approach. If you have the luxury to be able to acquire real measurement data, then go for it. So as I mentioned, you may want to severize, make it more severe, your PSD to reduce the test duration. So that's also an option in the software, or the opposite way around. Like if your shaker has limited characteristics, you may want to adjust the profile the other way around, like make your test longer, but with smaller levels, so that you account for the limited capacity of your shaker, right? So you make a wider use of your current shaker. No need to go for big investments if you realize that maybe that you can change a little bit the test spectrum and get it to pass on your current shaker. So that was for the accelerated vibration testing. Now we have this test spec. Say it's a PSD. We could use it on our shaker to drive our shaker test, but we could also use it in an FEA environment as a loading, as an input for our frequency domain vibration fatigue analysis. So let's take a look at this one now. So in terms of the different loading types, first of all, right, often the FEA analysis is done in the time domain, and people have in mind time domain. When we do measurements, it's all time domain. We saw that the standards mention PSDs and also shakers expect typically PSDs specification to drive a test. So depending on the sort of structural response, you may choose one or the other. Here we're interested in the dynamic structural response, like I think I mentioned it, the resonances and stuff. So it's very dynamic. So we'll go for the dynamic route there. And in that case, indeed, you can take time domain excitations or frequency domain excitations. By frequency domain, I mean either PSDs, as we saw so far. It could be also sine sweep or sine dwell, etc., etc. So the idea here is eventually to excite your FE model with those signals or spectra and simulate what's going on in terms of fatigue for the device under tests. So do you want to troubleshoot it? You want to do what if games? You want to check that the acceleration factor, you've brought it down to 12 hours test, whatever. Is it still representative of the operational environment? In other words, does it still replicate the same failure mechanism? You want to find out what the margins are. If you're running a 12-hour test, could it last 20 hours and still the battery pack would be intact, or the performance would still be applicable, things like that. And you want to understand why a failure might have occurred, and so you can avoid it next time by redesigning it. So how does it work in design life this time? So time domain excitation, you would typically run a model transient analysis. So this will give you the model coordinates that design life accept as input, and so this is a bracket. So we have the results of a model analysis. So in there we've got the model stresses that we combine with the model coordinates to come up with time domain stresses, and we can run our fatigue analysis, whether it's stress life, strain life. The nice thing with time domain excitation is that you could do things that that are more natural to do in a time domain. For instance, multi-axiality, you get a better understanding of multi-axiality, and also things like the contribution of each mode, to the overall damage is very easily done in time domain. But frequency domain is often faster, and everything is based on statistics, and it's closer to what you will do on the shaker, because it utilizes the same sort of inputs. So in that case, we've got our FE results files containing the frequency response functions. We've got our PSD here, or sine sweep, or frequency domain loading, and we superpose both to obtain the stress spectrum response at every node. Here is an example where you see two modes, and eventually the damage or the life distribution. So this goes again, in frequency domain, we could use power spectral densities, sine sweep, sine on random, sine dwell, etc. If you're using PSDs, I mentioned multi-axiality in the time domain, but in frequency domain it can be done as well. So we could use multiple correlated PSDs as inputs. So you need the autospectral densities and the cross-spectral densities, and you count this way for the various directions, multiple directions excited simultaneously. And this sort of analysis is also valid for Welds. So all the examples I've taken on this slide are supports or brackets, and some of them are welded. In this very screenshot, it's a solid weld that have been solved for vibration, for frequency domain fatigue, right? I'll do a demo of that one, like vibration induced fatigue. So this leads us to the third aspect, which is the structural fatigue. So the fatigue analysis of the vehicle structure. So as I said before, we may want to utilize the existing platforms or go for new architectures. But in both cases, we have to run a fatigue analysis of the body in white, or to check whether the changes we made to accommodate for the batteries are still leading us to a sufficient fatigue life, right? So here we use again design life, and it enables you to do that sort of analysis very easily, right? So you could have the model of your whole body in white here, including all the seam welds, the spot welds, and everything, the different materials, different junctions and stuff, and we apply the loads. Here, since it's structural, it's typically run in the time domain. Those are typically road load data that you could apply to the frame here. Of course, you'd model the weight of the batteries in there as well. And so, as I said, you can do the sheet metal fatigue or seam weld, spot weld, stress life, strain life, safety factors as well, Dan Vang's safety factor, or just a coefficient based on the fatigue limit, how far you are from that. The FEA can be linear or non-linear static. It can be also dynamic with model superposition. And again, time domain is often preferred, but if you want to go for the frequency domain because it's faster, then you can as well. So I rushed into many very interesting stuff, but each would require probably much more detail. So if you're interested to one of the topics I mentioned, don't hesitate to go on our website, ncode.com, then under About and Webinars, and you'll see a long list of recorded webinars, just like this one, that are more dedicated to one subject or another. For instance, you get the random vibration fatigue capabilities in nCode Design Live that was recorded this year. You can find there, still with fatigue, you've got the fatigue of Welds, or a webinar, or you've got a number of webinars to do with this shaker profile, design of the shaker profile, like this one, improving shaker tests to deliver reliable products. So check those out. They are freely available from our website. With that, I'd like to move to the demo phase. So very quick demos of the various things I mentioned. So the first demo I'd like to run is to do with the vibration profile design. So here I've got two inputs, right? The input on top is coming from our database of vibration profiles. So it's pointing to a spectrum here, this one, right? And this spectrum can be found if you go in Vibration Manager, you'll find a number of standards there. And I think I picked one from the USA BC battery tests. Must have picked this one. So loads of information, the test duration, the units, etc. You can graph it, etc. And actually in the software, you can point to it. So that's what I did. Then this is just a table of a few breakpoints. So this vibration generator glyph now samples it into like 4096 frequency lines so that it can be used in various analysis. The second input is some measured data, right? So real measured data. It's either one test track or the concatenation of many test track. It's up to you. There are different ways of using a glyphworks to constitute, to construct your whole mission profile. In this example, let's say it's a concatenation of a few events here, and I'm taking the PSD of that signal, and here I'm comparing the PSDs. Are they really comparable directly like that? I'm not sure. The red one, which is coming from the standard, is meant to last, I think, 3 hours, whereas this is the PSD of a few 100-second signals. It's not directly comparable. You should compare something that's in the same domain, right? That's really comparable. So what I did here, I produced what's called the fatigue damage spectrum for the standard spectrum from the standard, and I did the same for the spectrum from the measurements, right, from the measured data. And I take into account the duration of this red spectrum here. And in here, I'm saying that my whole measurement, my whole mission profile is actually, I can't remember, 30 hours or something. I wrote in there, yeah, 30 hours. So now what I'm comparing is the damage after 3 hours of the spectrum from the standard with the damage after 30 hours of this signal. And that's the interesting bit. So that's fully comparable, right? And if I look closer, so the red curve is the fatigue damage from the standard, the blue one is the measured damage, and you see that there's some crossing here, right, at the low frequency end. So the nice thing is, let's envelope those frequency, those fatigue damage spectra. So I'm enveloping the two fatigue damage spectra, and it's on the envelope that from the enveloped fatigue damage spectrum that I'm trying to derive a test, a PSD that will last for 3 hours. So I'm coming up with a test of approximately one GRMS, and I'm overlaying this test that I just derived with the original test spec from the standard. And indeed, so my new test spec is in red here. The test from the standard is in blue, and indeed, my new test spec has somewhat higher levels at the low end frequency end to account for the crossing that we saw earlier. So I could use the red one to give as input to my shaker or to my FEA based fatigue analysis, right? So this is a very quick demo just to show you the look and feel of the software. It's got a very logical way of building a workflow. If you double click on each of those icons, you get a number of properties that you can act upon, and you can save that and share that with your colleagues. It's very easy to use. Let me move on to the next example. Here I've got a bracket, different property groups, and as you can see, there's apparently a seam weld here in red, and I've got 3 directions of excitations, X, Y, and Z, that I've picked from the same standard again, and I'm associating it all in this analysis glyph here, and eventually I'll see my distribution of life, my contour plot of life for the welds, right? So you see where your weakest weld is and what's the corresponding life or damage. You've got tables of results associated with that. Obviously, you can change the material. You get loads of fatigue properties you can set up in this glyph. I won't enter into much details here, but just to show you again, the sort of things we can do in the same interface, meaning that this PSD, which is currently coming from the standard, I could have used the PSD I measured instead, or the envelope that I just calculated, right? So it's very, very flexible. And the last demo was a demo to do with the full structure. So, here in this case, it's 25% or something of a body in white. And I chose here to run a time domain analysis. It's a strain life analysis, and I limited the analysis to just the shock tower. And we see here the contour plot of damage of just the shock tower. Again, loads of properties you can enter in there to account for surface finish, multi-axiality, etc., etc. So that's pretty much it that I wanted to show you. Again, if you want to know more about any of those aspects, check out our website, send me an email. Let us know how we can help. I'm aware that I went very quick. So many interesting things to be mentioned here. You can't enter into each and every details of it, but feel free to contact us.